All right, all right. Party people, thank you for joining us. I am Ellis. I'm the president of Web3 and AI at Hacker Earth, and we are super excited to be hosting the SAY All-Star Hackathons for both the college edition and the high school edition. Joining me today is Alex from the SAY team. Alex will give a little bit of a background on himself, and then we're going to be doing a deeper dive into the SAY stack. Alex, let's say hi.
Hi, thank you. Thanks for being here. My name is Alex. I'm DevRel at the SAY Foundation. And today we're talking a lot about the architecture of SAY and what's going to come in the future.
Awesome.
Yeah.
Oh, sorry. Well, with that, it sounds like you've got some stuff to cover, so I'm going to bow out.
Yeah.
Whenever you'd like, just tell me and I'll throw the slides up on the screen.
Yeah, you can throw them up already. We got a lot of stuff, interesting stuff to cover today, which let's just do like a small recap, which we can do for each time for these kinds of workshops. For those of you who are new, SAY is the fastest layer 1 blockchain featuring EVM. Our current stats are 400 millisecond block times, a lot of daily active accounts, low fees, parallelized EVM, and around 12K plus TPS at full speed. Plus, I'm also going to talk about the Giga upgrade later on. So that's a lot going deeper into the architecture of SAY and what's going to come for the future. But right now, let's focus on what SAY has right now and what the current state of SAY is architectural-wise and what tricks that we have to make SAY as fast as it is. So I'm going to go into all of the main tricks that we have. These are not extremely complicated to explain, while they're actually pretty hard to implement in practice. So stay tuned for the explanations. They're rather interesting. So one of the first tricks that we have when dealing with transactions is actually the fact that in classical EVM, transactions are linear, so they're not really parallelized, they're done in serial. So now the question really becomes, if we want to make transactions with EVM much faster, how would we do that? And our first principle that we do is something that we call optimistic concurrency control. Sounds pretty fancy, but the principle is extremely easy to understand. It essentially means, as one of our first tricks to parallelize the EVM, is to simply do an optimistic execution of our transactions and then check if they are actually valid or not, and if they are actually coming into conflict with other transactions in our block. So in this concrete example that I have here, you simply have like a few transactions, transaction 1, transaction 2, transaction 3. And using optimistic concurrency control, what it actually does is it just pretends at first that all transactions are independent of each other, which in a concrete example means, for example, they don't touch the same state, they don't touch the same accounts, they don't touch the same nodes, meaning they are independent of each other. They would be independent of each other. So first of all, it just pretends that it's actually independent. It tries to execute them, and then it actually checks if all of these transactions in that block are actually colliding or not. Meaning, after execution, did they actually touch the same state, the same nodes, the same account, the same balances? In case that happens, so if there's a conflict, so for example, our TX3, for example, has a conflict because it touches the same state as transaction number 2, what it actually does is it actually re-executes transaction 3 after it executed transaction 2. So it executes transaction 2, and then it will come back and try to execute transaction 3 again, and then validate that the state transition has been correct in the order that is supposed to be. So that's one of our first tricks on how we make the parallelized EVM as fast as it can be. Next, essentially, is the next question. So since we can execute these blocks extremely fast, how would we then execute these blocks as fast as we can? So we have a lot of these transactions parallelized now. How will we actually do it in a fashion that we can include these transactions as fast as we can in our blocks? And this is actually pretty simple to understand. The fact lies in how these blocks are actually generated. So in your normal Tendermint consensus, which is just a normal Byzantine fault-tolerant consensus. It just means what we have is we essentially have multiple stages. So we have, on the left, you can see the normal way of doing it. And then on the right side, we actually see how SAY is doing it. On the left side, you see we actually have a propose phase, a pre-vote phase, a pre-commit phase. So that's essentially just all of the validators who actually create these blocks, just gossiping between each other and just agreeing on what is correct and what is not. And at the end, they are actually finalizing their block and processing it. And that takes some time. So the thing is, as long as there's a propose, a pre-vote, and a pre-commit happening, there's nothing happening in between. So no one is actually computing a block and just finalizing a block, which when you try to actually squeeze out as many milliseconds out of this is actually not really efficient. So what you can do instead is pretty simple. Instead of waiting for the pre-vote and pre-commits to actually come in, you optimistically, again, this is another really nice concept. We optimistically assume that this pre-vote and pre-commit is correct, and we compute the whole block optimistically while the pre-vote and pre-commits are happening. So these voting stages between, so the gossiping between these validators is happening. Each of them is on their own, finalizing their block themselves, and then they're essentially checking against it if that was correct or not. Of course, if it wasn't correct, it takes more time, so we're gonna revalidate it. But of course, in the mean case that all validators behave correctly, this greatly improves the execution time. So you essentially just shave off 200 milliseconds by just doing that trick. And now we can execute it pretty fast. Now we can actually have them included, or transactions included in a block really fast. Next question really becomes, how do we actually handle all of this data, right? Because what we have here in the back, when I go back, is we have 400 millisecond block times, and we have a lot of transactions that get included into blocks since we are able to handle this amount. Then the next question really becomes, naturally becomes, what do we actually do with the state? Because there's a lot of transactions that need to be included into a block, and how do we handle all of that state data? So just to recap the whole idea, it's essentially what the state really is, right? It's account balances, it's smart contract states, it's nonces, it's addresses. So all of the data needs to really persist, obviously, to process new transactions and generate a state root that we can actually verify. The state root just being basically the last state in which we build our stuff on top of. Now, naturally, this obviously becomes a problem, because as we just have more throughput, more transactions, we're just gonna get more state, and that state is just gonna bloat up. So we're just gonna have way more. So we're gonna have a huge state, a huge store state. So the state storage obviously gets way too big, so we have too much data, and we're gonna have a problem actually with nodes actually keeping up with the amount of data that they actually have to handle. So how do we prevent this state bloats? Idea is, again, simple. The idea is pretty simple itself, but it's actually really hard to really execute on. But we achieved that, and it's actually a really, really clever idea. It's to prevent that state bloat. What we do is we do a memory mapped IAVL tree. That sounds harder than it actually is. What we actually do is we take parts of that tree where the data is stored. So we have a memory mapped snapshot of a key value store, leaves, and nodes. Sounds harder than it actually is. It just essentially means you're just basically making a huge tree of data, and that data and that tree contains all of the data that you can then subsequently verify by going to each node and each leaf, and then verifying each part of it. Now, the complicated part really lies in the fact that this usually is all on a hard drive, on an SSD, on just some persistent storage, and that makes it slow. So what we do is we just take a memory mapped IAVL tree, we take parts of that, put that into memory, and then we can essentially, in that, as you see on the left in the workflow, we have the transactions that we extract them, we do a change set. That means we are looking at what's actually going to be changed, and then we're doing an async commit to override a head log. That sounds complicated, but it just essentially means we are writing that stuff into memory, and then when we have enough time later on, when all of this is done and finished, all the calculations are finished, we're just writing that stuff to disk when we have more time later on. So in practice, we are having all of the advantages of having the stuff essentially all in memory, while we are also having, of course, the advantages that the stuff is that everything here is completely retained on disk later on. So we have an in-memory state root creation, we write it to a write-ahead log, then to disk. And by doing this, our commit times are just getting, over 280 times faster. And by doing this, we are having both advantages of both things, right? We don't have to store everything in memory or so. That would be way too complicated, way too big. And we don't have the problem of having to read everything from disk all the time, which slows us considerably down. And by doing this, we can accelerate the transactions, as I've said, by all about commit times by about 287x, to be exact. And another trick that we're doing is we are rebuilding this stuff from the ground up. So what we also did is we essentially just, when constructing that memory mapped IVL tree, we make sure to actually try to reduce metadata as much as we can. So that way we can improve state sync. So essentially the method of which most nodes get to the block tip, also by around 10x. Exactly. So by preventing that state bloat, we are essentially having what we are calling SayDB. And using SayDB has it really made a huge difference when we are talking about our node performance. So we really had like block times going, staying at 4 milliseconds, but the nodes themselves could catch up to blocks like I'd say around 10x faster. And that really was the difference when we had a lot of work with our RPCs and our indexes, which I'd like to thank as well. So yeah, this is the current state. I think what would be super interesting for most of us here is what are we doing to push the boundaries of what we have, right? We can't be staying at the current state and just be lazy at that point. I think what's really important is how do we push the boundaries to the next level, and this is essentially what GigaSay is. This is the I probably assume that you probably saw it already in the blog post on Twitter already. But just as a visualization of what actually GigaGas means. Gas, in that sense, is just the normal gas unit that you know from Ethereum, right? So there's one gas unit. So for example, in the comparison that we have here, we're just comparing the normal Ethereum L1, which is around 60 TPS or around 1.25 megagas per second. Then you're gonna go like to most L2s, which have like 10 megagas per second. So around 500 transactions per second, assuming we have like a normal EVM transaction, which is like 21,000 gas units. And then we're gonna go like into more of the high throughput EVM chains today right now, which are like 100 megagas per second on mainnet. And then there's gonna be us, which just take a look and how much more this is going to be, which is at least going to be 5 gigagas per second, which right now is 250k transactions per second. But I really like to focus on the gigagas aspect because most transactions on Ethereum are going to be way more complex than just normal simple EVM send or receive transactions or anything. They're really going to be complex transactions interacting with DEXs, with all kinds of dApps that we have on Say. So our emphasis really lies on the fact that we're actually going for gas. The question now really is, how are we actually going to do this? And the approach is, again, simpler explained than it actually is in practice to pull off. It's extremely interesting how to do it. I will actually give you some resources right after this presentation so you can actually take a deeper look into this. Say Labs is extremely proud of what they're building right now, and I think it's going to be fantastic. First of all, the main idea behind the GigaSay approach is that we completely redesign the whole structure of how we actually approach nodes. Because in the future, or back then in the past, we actually looked at just a node that just that does everything at once. So it executes transactions, it validates transactions, and it receives RPC requests and sends them out. So that was the usual approach. But when trying to actually optimize for going into GigaGas realms, you really want to be as optimized at every stage as you can. So really it's a complete redesign. And the idea behind this really is you kind of split it up into 3 parts, which at the top you can see in the graphic is executor nodes, which is then the second one is validator nodes, and the third one is edge nodes. The executor nodes are, simply put, just the nodes that just execute EVM transactions, and they're not going to handle anything else. Then we're going to have validators who actually take care of ordering consensus and making sure that they actually produce the blocks. And then we have the edge nodes, which only take care of basically everything coming in from outside, which is your just initial validation of transactions that come in, your RPC interfaces, your just payload simulations, or like whatever you need to do essentially when interacting from outside with the whole thing, with the whole chain. This is what edge nodes are mainly doing. So by splitting this up, you are essentially giving validators and the executors a chance specifically to be as fast as they can while not being interrupted by anything else that comes in. And by doing this, we can really make the validators as efficient as they can be. And specifically for GigaSay, there is going to be a very nice consensus algorithm that, as far as I know, hasn't been used in this particular manner. And it's actually called the Autobahn. So if you don't know what that word actually is, Autobahn is actually the German word for highway, or interstates, probably more interstates. And what the German Autobahn actually has as a special feature is there's actually no speed limit on a German Autobahn. So most parts of the German Autobahn actually do not have any speed limit technically. And this is exactly what's going to enable us to be as fast as we can. There is essentially no brakes on this. So using the Autobahn algorithm is actually, or the Autobahn consensus mechanism is actually a bit harder to explain. But key ideas really, there's really 2-3 key ideas, which is that you have validators who actually produce blocks themselves independently and attach a proof to it. So you have each validator at the top, like you just see like 4 lanes, each of them is a validator, and each of them maintains a dedicated lane of blocks. So we visualize them just as cars. Essentially, we just have like a dedicated lane of blocks. Each of them produces blocks, which are these just cars driving on the Autobahn on each lane. And then we actually share these blocks with each of the peers in the network. I actually just saw that comment. Yeah, if you're German, this is actually quite a funny coincidence. But yeah, Autobahn is just extremely fast, and this is exactly what it's going to represent. So yeah, each of that is essentially shares these blocks with their peers in network. And what it also does is it provides them a proof of availability, so a POA to the current leader. That's really important because it means that once you actually, when a validator actually makes a block, it actually gives you a proof attached to it that tells you, okay, this has been already computed. I don't have to like do it 10 times. So that makes obviously the future steps much easier, which is one leader. So what we have is we have essentially our validators who just produce blocks by their own, attach a proof to it, and then we have each of the validators in the end, they all together choose one leader. And what that leader does then is it just rotates around. And that leader then periodically cuts across all of the latest blocks from each lane. So what you essentially do is at one point it decides, okay, we have enough blocks. Let's cut. And we're just going to cut all across all lanes. And at that point, it initiates a voting round for each tip. And then, for example, for the tip cut 2, 2, 2, 3 means we have 2 cars at the top, 2 cars in the upper middle lane, then 2 cars at the bottom middle lane, and then 3 cars at the bottom lane. So as you can see, essentially this is like 2, 2, 2, and 3 then. So by doing this, the leader can then, pick up essentially all blocks that are that need to be included. And then what you can do is for any given tip cut. So at that point is essentially we said, okay, we have all of our cars here, and now the leader picked like his tip that he wanted to include. And what he then lastly does is essentially we have our blocks and now we're going to just order them. So the leader will order them. So for any given tip cut, the order of the blocks is determined deterministically through the voting round. So what they will do is essentially they will say, we have these and these kinds of blocks. The leader pick the tip, cut it off, and then at that point, all of the validators are going to vote on that directly. And by doing this, you essentially have two advantages. The main advantage of this is obviously we're going to be extremely fast because each validator produces their own set of blocks, so he doesn't have to wait on the others to actually confirm what he's doing. And on the other hand, you still have the advantages of actually having obviously a direct consensus on what actually happens to be like the block or the chain of blocks that you actually produce. So you still have the advantage of actually being parallelized in almost every aspect, while also having in the end a deterministic block chain really of blocks that actually come out of it without actually having to sacrifice anything of the others. So yeah, the consensus mechanism itself is actually pretty interesting. The leader itself, so in that case, it's like the one with a crown, proposes a cut. The validators vote on the whole thing. Then a certification of each of that requests requires at least F+1 votes. So you need to at least have like probably more than 50% of it. Details of this like on the block. It's just a simplification at that point, but just to at least you have to have a majority of votes. And the idea behind this really is like you essentially the one that actually cut the tip proposes to the other validators what to vote on, and then they can actually vote on the whole thing. And then this is actually also quite funny because they actually like having these funny car references. You actually get in the end this is actually a certification of available requests. So in short, it's a car. So it's a car on the Autobahn. So that's the whole pattern behind this. Exactly. So what I would definitely recommend when this was a bit too hard to understand at first, I would definitely recommend going into the blog post afterwards. I'm going to also list that. But really the key idea that you really should take away from this is you are having each validator making their own blocks. And then in the end, there's one leader who actually says, it's time. We're just going to collect what we have. And we're making a decision on what's actually going to be in the final order. And the rest of it is extremely interesting, I gotta say. A lot of interesting math, a lot of interesting computer scientific topics just to make that stuff actually deterministic and just extremely fast in practice. So yeah, now let's go to the benchmarks a bit because, you can theoretically formulate everything in there, but I think the most interesting fact is really this is not even in theory, is this really fast, but the thing is this also actually fast in practice when you actually introduce latency, when you introduce liveness problems, when you introduce essentially all of the real world problems that you have, right? Only at that point you can actually make sure that this concept will actually work. And so what we already have is, and this is also what I've been showing in the beginning, and what is also, probably have seen somewhere else already, which is just a benchmark, but I want to really go into it and actually explain what's happening. So really what you want to look at, of course, is obviously the big number, which is like 5.4 gigagas per second. But what you actually also want to watch out is actually the fact that this is actually already a test with nodes and endpoints and validators that are actually distributed across several regions. So if you look at it, like this here is, one of them is in Southeast Asia, one of them is in EU Central, so probably Frankfurt. And then you have like several in US West and in US East. So that means even in a real life scenario where you would have a lot of transactions with validators that are actually distributed across continents, right? So on the other side of Asia, on the US, East Coast, West Coast, and in Europe, Central Europe, you still have like at least 100 milliseconds of ping and delays, and even a latency. And even then, in these higher latency regimes, you still have an extremely high amount of gigagas that can be pushed through the whole system. So I think that that's even one of the most important facts here. It's not even that it's just 5 gigabytes per second. It's actually in a committee distributed way where we actually have a lot of latency introduced and actually a lot of packet drop introduced. So as you can see, the transactions per second, obviously the executed TPS, so that's the one that actually executes the EVM transactions, is actually the slowest because it actually has to just bear so much data from the state. And then our edge nodes is, and the stream nodes or the validator nodes are pretty much on par with 170,000 transactions per second. But yeah, I think these benchmarks are only going to get better, and I would, I can definitely say that. Yeah. Stay tuned for more information coming about GigaSay. So Say Labs will slowly give you way more insight into how it works in our case in Say, what the difficulties were, and also how it will exactly be set up. So I would definitely recommend a view into the docs on some more of the, let's say, on the current state of Say for Say v2. And if you want to take a deeper look at what we have for Say v3, then I would definitely, give a warm recommendation to the Say research page, which is www.sayresearch.io. And they basically going to have, Say Labs has a lot of super interesting articles on how we're actually going to pull off Say v3. And of course, just join Discord and follow us on X if you have more questions. And of course, you should also follow the Build with Say account if you have more questions coming for the hackathon, just in general.
Well, I was muted. Awesome. Alex, that was rad. That's pretty much all I can say. Very thorough. This, for any of the viewers that are out there, anybody watching live, this will be recorded. This will also be posted back on the Say as well as the Cracked Labs YouTube channels and available on Twitter or X for you to consume whenever you want. Again, fantastic job. Think there's a lot more to go through. We have a couple more workshops that are scheduled for Say. The next one is going to be on DeFi, and the host is going to be Owen on that one. So excited. And in between now and then, hope everybody has a successful build. If you have questions regarding integrations, contracts, or just general questions for the team, do not hesitate to reach out to us on Telegram. There are different channels for each of the different topics. And if you need anything, again, just feel free to shoot us a DM and we'll get back to you immediately. And with that, guys, let's call it a day. Again, thanks everybody for your time. Alex, great job. And we will see you at the next webinar.